We'll now start to determine the polarity of polyatomic molecules. For diatomic molecules, it is easy to determine their polarity since only one bond is involved and their molecules are linear. This is not the case for polyatomic molecules since many bonds are involved with molecules of different geometry. So let us start first of all by introducing to you the concept of dipole moment. Dipole moment, this is a measure of the degree of charge separation in a covalent bond, and its unit is called dBi. This molecule here is used to exemplify this concept. We know that chlorine is more electronegative than hydrogen, and therefore there is some degree of charge separation here. So we say a bond dipole is created. Here you see an arrow, and the point of the arrow is towards the chlorine atom. Always when you represent a bond dipole moment by means of an arrow, the arrow is always pointing towards the one that is more electronegative, and there's a little plus sign there that is with the one that acquires a small positive charge. That is what we have spoken there about. Dipole moment is a vector quantity. You will do this concept when you do forces. It has both magnitude and direction. Magnitude is the degree of charge separation. Of course, the direction is that where the arrow is pointing. So what we're seeing here is this. We've spoken about that already, but he puts it in perspective a little bit more. So you say a bond dipole can be likened to a vector. If the peripheral atoms are more electronegative than the central atom, we can say that each peripheral atom is exerting a pulling force on the central atom. If the central atom is more electronegative than the peripheral atoms, then we can say that the central atom is exerting a pulling force on the peripheral atom. The resolution of these forces on the central atom can be used to determine if the molecule as a whole is polar or not. To do this, the following highlighted points must be considered. All right, listen to this now very attentively. If the resultant force on the central atom is zero, the molecule will be nonpolar. In this case, there is no resultant dipole. The following vector diagrams are used to illustrate this point. A black dot is used to represent the central atom, and lines are used to indicate the pull or push force on it. The lengths of the lines represent the magnitude of the forces, degree of charge separation. So I want you to inspect these forces here, these vector diagrams here. So this is the central atom here. Now let us suppose that these here are the peripheral atoms. So in this case, what we are saying here is that the central atom is more electronegative than the peripheral atoms here. We can thus say that there are three equal forces separated by angles of 120 degrees pushing on the central black dot. In all of these cases, if that was the central atom and these were peripheral atoms doing all these pushing and pulling there, the central atom will not move, and therefore the resultant force on it will be zero. In such a case, the molecule will be nonpolar because there is no net shift of the electron cloud in any direction. If the resultant force on the central atom is greater than zero, the molecule will be polar. In this case, there is a net shift of the electron clouds in one direction with a resultant dipole. So let's look at these examples here. There's a black dot. Here's a vector that's moving in this direction and one in that direction. But here you're seeing that this vector here is bigger than that vector. Therefore, there'll be a resultant force moving in that direction. If it were a molecule, say this was a central atom with an atom here and another atom here, and this one here is having a higher electronegativity value than that one, then there'll be a shift of electron in this direction, and therefore the molecule become polar because this side will develop a slight negative charge and that will be a positive charge. Same thing here. In this case, what will happen with the black dot? Everything is pulling in this direction, so there's a resultant motion in this side is resultant dipole here, indicated by the red arrow. So similarly, you can have a central atom here. Two of the peripheral atoms here are pulling in those directions there with a strong force, and this one here is weaker than that one. So this one, the central atom is really pulling on that one there. But these ones are pulling electron away from this central atom. And in such a case, the molecule is going to be a polar molecule because there will be net shift of electron cloud in this direction and in that direction there. Okay? Let's see what's happening there. Here you have a bent molecule. Here's a black dot. One force like that, one force like that. It will be a resultant force in that direction there. If it's for a polyatomic molecule, oxygen and fluorine here and a fluorine there, each fluorine is pulling like that, pulling like that. Therefore, there will be a shift of electron cloud in that direction. Each fluorine atom there will get a small negative charge, and this one here will be left with a little positive charge. Now this one here, 4 vectors, 2 of them like that, equal 90 degrees. So these ones here will overwhelm these ones because they're stronger, and therefore there will be net resultant force in that direction here. So what is going to happen if you had a molecule with 4 peripheral atoms, and 2 of them are pulling strongly in that direction, more than these are, there will be a net shift of electron cloud towards these atoms here, and they'll be drawn away from these. So that end of the molecule there will be slightly negative, and this end is going to be slightly positive. Okay, I hope that will help. So let's see a molecule and then put in the forces inside here. All right. Here we're using carbon tetrachloride, CCl4, okay, to illustrate this concept. That's 4 chlorines there, okay? Now this is our central atom now. We know that each of these here has a bond angle of 109.5. Because chlorine is more electronegative than carbon, each of them will pull an electron away from the carbon, right? We can thus say that there are 4 equal forces separated by bond angles of 109.5 degrees pulling on the central carbon atom. What is going to happen here? The resultant force on the central atom will be 0, and therefore all of these will get cancelled out, and we say that this molecule here is nonpolar. So we can make a general statement that any AX4 molecule will always be nonpolar. We just put in those negative charges here for you to see. That would have acquired a positive charge, negative charge, but in the end they cancel out each other. All right, let's see some other molecules now. Let's look at this molecule now. This will be called an AX because you're having 3 of these the same. Okay, AX3, 1. So this is slightly different from that one, no? Why is it? Because this fluorine here is more electronegative than this chlorine here, right? So there will be a resultant net dipole in that direction, because this is a strong force pulling like that. As a result of that, this fluorine end here will be slightly negative, and electron will be pulled from that area going in that area there. This will be a polar molecule, and this is the ball and stick diagram there, model for that. All right, AX3E molecule. This is like ammonia. Let's inspect this molecule now. Nitrogen here is a central atom, and it is more electronegative than the hydrogen atoms. Therefore, it will pull an electron in this direction, okay, towards itself. We can thus say that there are 3 equal forces separated at bond angles of 107 degrees pushing on the central nitrogen atom. The net result is a shift of the electron clouds away from the hydrogen atoms towards the nitrogen atom. Each of the hydrogen atoms acquires a small positive charge, and the nitrogen atom acquires a small negative charge. The molecule is thus polar. So this molecule here as a whole is a polar molecule. All right, so I hope that helps. You can read that. You can read the writings that they've done, the whole description and everything. Leave some time for you to read that. I'm not a good guy at reading back things that I wrote. Getting old now. Polarity of AX2E2 type of molecules. We'll use the water molecule to exemplify that. So here we're now having water molecule. Here the central atom, of course, is oxygen. Oxygen is more electronegative than hydrogen. And we can say that it's pulling electron towards itself from the hydrogen atoms here. So as a result of that, this end here is left with small positive charges, these two ends. And because the electron is shifting towards the oxygen here, that end of the oxygen will acquire small negative charge. And of course, if we use forces here, there's a pushing force there, there's a pushing force there, there's a net dipole in that direction here, and it is shown inside this ball and stick model here. So water molecule will be a polar molecule with the hydrogen ends being slightly positively charged, and this one here will have a slight negative charge here. Okay? Alright, that is a AX2E2 type of molecule. Let's look at the AX2 type of molecules. We use carbon dioxide to exemplify that. Remember we said that this is considered to be a single bond. When you have double bonds, it's considered to be a single bond. Here's a central atom, and here you have a linear molecule. We have already determined that carbon dioxide is a linear molecule when we did shapes of molecules, right? So carbon dioxide here has a central carbon atom here with two oxygen at 180 degrees away from each other, linear molecule. Oxygen being more electronegative than carbon will pull electron away from that, and this will pull away electron from that. Carbon is expected to become positive, but because this dipole is equal and opposite to that one there, their effects will cancel out, and therefore no net charge will appear on this. And this is the ball and stick model there, and you can see we've put no charge on them. So anytime you have a linear molecule like that, okay, AX2, there's no lone pair there. If a lone pair comes on there, it's a different ball game now, okay? Because if you put a lone pair here, as happening in sulfur dioxide, you are going to get a bent molecule because this lone pair here will push these down a little bit, and it will affect the polarity of the molecule there. In such a case, it will become polar because of the new shape of the molecule. So I've explained that already. Now, AX3 type of molecule, you can use EF3 for that. The boron is a central atom. We have already determined the shape of this molecule. We say a trigonal planar molecule, and the bond angles here 120 degrees, okay, each of these. Now you're having three dipoles, and each of them is pulling away at this central atom at 120 degrees away, so each of these dipoles is equal. So in this case, because of this equal pull in every direction, they will cancel out each other because this guy will not move. Remember, one of the things you said is that if the central atom moves, then the molecule is polar. If it doesn't move, the molecule is non-polar, and this is your ball and stick model there for that. You can stop your video and read that whenever you want. You can go back, look things again. What do we have? Here you had, this is boron again. Instead of fluorine here, we put in two hydrogen. What do you think will happen? Fluorine is highly electronegative. Okay. If you had a fluorine and fluorine here, nothing will happen, but now there's a movement now, okay? Because this dipole is stronger than these, it will pull more electron toward the cell. These are pushing there. The central atom will move, moving in that direction there, and your net dipole is going to be in that direction. Molecule will be polar. These ends here are losing electron cloud. That end is gaining electron cloud. That part becomes slightly negative, okay, and this part becomes slightly positive. So polar molecule. So here's a summary of what we've done. Here are the AX4 type of molecules. This is a Lewis structure for that structure. You have 4 bonded atoms, no lone pair. This is the arrangement of electron pairs. That's the electron pairs, one that is 1 electron from carbon, 1 from hydrogen. You can see it's tetrahedral. Molecular geometry is that. Bond angle is this. These are all cousins. Okay, carbon is in group 4A and silicon is also in group 4A. Anytime you have carbon surrounded by 4 identical, or a silicon surrounded by 4 identical atoms, okay, same atoms, you'll have the same feature like that of methane. AX3E. Example given there is ammonia, is a lone pair here. So now you have 3 bonded pairs and you have 1 lone pair here. Okay, 1 lone pair. This is a lone pair here. Now, again, the electron arrangement is tetrahedral. When you talk about electron arrangement, you also include a lone pair here. It will be tetrahedral. The shape now, of course, is different from that. It's a trigonal pyramid. Bond angle, 107 degrees. Nitrogen, all these are cousins of ammonia. Because phosphorus is also in group 5A of the periodic table, and will form 3 bonds and retain 1 lone pair of electrons. So anytime you have nitrogen or phosphorus surrounded by 3 identical atoms, the molecules have all these features here. So go up a little bit more. AX2E2, like water. You have 2 bonded pairs, you have two lone pairs. There here are. But again, the electron arrangement with tetrahedral, because I took time to point out to you, these here are where the bonds were before when you created it. So they have tetrahedral arrangement here. But it'll be a V-shaped molecule or bent molecule. Okay, remove that one there, put in a lone pair here. Alright. Bond angle slightly less than that because these lone pairs here are taking up more space and they're pushing these a little bit more forward, a bit down. And these, of course, will be hydrogen sulfide, OCl, okay, group 6A atoms. If you have 2 identical atoms to react with, in the case of water, sulfur, and this one, or oxygen and chlorine, they have similar features. AX3, boron trihydride. You have 3 bonded pairs, no lone pair. See, be careful. You must indicate whether or not it has lone pairs. Look what happens if you had a lone pair there. See, look, see, there's a lone pair here. Because of that lone pair, this thing here is a trigonal pyramid because that lone. Remove this lone pair here, and this guy becomes exactly like this because there's nothing here to push these legs down. You see that? These bonds down. So it flattens out and it becomes exactly like trigonal planar, 120. All of these. Aluminum will follow the same thing. Aluminum is just in the same group. And you have 3 identical atoms with anyone with either this one or this one, you'll have the same pictures like this. Of course, AX2, okay, 2 bonded pairs, you count this as 2, right? 2, 0, linear, 180 degrees, BeCl2, and this one here. Here is an assignment I have for the students here. You can do that to your own solution manual has the answer to that. Okay, so I hope that was helpful for you. I'll see you next time.